Okay, so let's continue from where we left off last time. We were talking about continuity. So recall that a function, you already have this in your notes, is continuous at an x value c if three things are true. One, f of c exists. The limit as x goes to c of f of x exists. And that these two things are equal. I'm sorry. Yeah, this should say exists. And what I should write up here is defined. Instead of exists, we'll say it exists for limits, and we'll say that the function is defined there. And we saw various ways that a function may fail to be continuous at a certain x value. Discontinuity is failing to be continuous. We saw that discontinuities sort of fall into two rough categories. We have the removable discontinuities, in other words, a hole in the curve. We saw examples of that. Hole in the curve at x equals c, whether or not the function is defined someplace else or not. And we saw all other kinds of discontinuities were called non-removable. But we could further classify the non-removable discontinuities. We saw various different kinds of non-removable discontinuities. We saw the jump discontinuities, where the function is sort of merrily moving along, and then at a certain x value, c, it just jumps. We saw the infinite discontinuities, or the vertical asymptotes. So VA, vertical asymptote. You've seen lots of those over the course of your mathematical careers. Here we are at x equals c. And we also saw that strange oscillatory discontinuity, where the curve oscillates faster and faster and faster, infinitely fast, as we get closer and closer to the x value c. And I showed you an example of that. We have something that looked a lot like this. Remember, the important point when you sketch something like this is that it oscillates sort of infinitely often between, say, here and the point where you have your discontinuity. I'll draw it at 0. And we could talk about these in terms of limits. We could talk about these. Looks like you're still writing. Let me slow down and give you a chance to catch up because there's a lot of drawing on the board. So at a removable discontinuity, the limit exists. As we get closer and closer to x equals c, we're getting closer and closer to that value, whatever it is. Well, call it whatever you want. At a jump discontinuity, the limit doesn't exist because the limit from the left and the limit from the right are different. We have a perfectly nice limit from the left at this height. We have a perfectly nice limit from the right at that height in this picture. So the limit from the left and the limit from the right are not the same. In infinite discontinuity, the limit from the left and or the limit from the right are infinite. And in an oscillatory discontinuity, even the one-sided limits don't exist. They just go crazy. Okay, let's talk about continuity on an interval. So we know what it means for a function to be continuous at a point. Now I want to talk about what it means for a function to be continuous on an interval. Wish I had more board space. We say a function f is continuous on an open interval AB with parentheses around them if f is continuous at every point, every x value in the interval AB. We know what it means to be continuous at a specific x value. If you're continuous at all the x values in A and B, we just say the function's continuous. And intuitively, when you see the word continuous on an interval, you should just think, oh, well, this function, if I draw its curve, the function has no breaks. It's an intuitive idea. So say here we are at A, here we are at B. The function's continuous on the interval. I can draw the curve without picking up my chalk, pencil, pen, whatever from the writing surface. It has no breaks. That's what it means to be continuous on the interval. Now, it's a little bit more challenging to define continuity on a closed interval because you can't define limits at the endpoint, which means that the definition of continuity needs a little bit of adjustment. So we say function f is continuous on the closed interval AB, this time with brackets, if so this time all the way between A and B, including A and B, if f is continuous everywhere between these two, so in other words, on the open interval, which we already defined, secondly, that f is continuous. Oh, sorry, my bad. Limit as x goes to A from the right. If we have an interval from A to B, the only way you can approach A in that interval is from the right. Limit as x goes to A from the right of f of x is equal to f of A. And we have a condition like this at the other end. The limit as x goes to B from the left of f of x equals f of B. This time, f is defined on the whole closed interval. The first part just says it's nice and continuous inside. We can draw the curve inside with no breaks. The second part says that as you get closer and closer to x equals A from the right, the curve gets closer and closer to the circle here. So none of this nonsense. You can't have like an open circle and then this up here. That's what this is designed to get rid of. So we have a closed circle here. This closed circle actually goes at the end of this curve. And this says this closed circle actually goes at the end of the other end of the curve. So, properties of continuity. If f is continuous at, let me say, if f and g are both continuous at x equals c, so is f plus g. You have two continuous functions at a point. Their sum is continuous. So is f minus g. F plus g and f minus g are both continuous. So is c times f, where c is just a real number, any real number. So is f times g. And so is f divided by g, so long as we have our usual caveat, so long as g of c is in 0. If g of c is zero, then no. So we can start building a library of functions and talking about where they're continuous. All polynomials, doesn't matter how high the degree is, are continuous everywhere. Now let me go with this. All rational functions are continuous, except at points where the denominator equals 0, where they have vertical asymptotes or holes in the curve by that. So they're continuous everywhere except at those points where the denominator equals 0. And at those points, we could either have a vertical asymptote or we might have a hole in the curve, depending. We've seen examples of both. Sine x, cosine x, these are continuous everywhere. Exponential functions are continuous everywhere. There's a lot of functions which are continuous everywhere, or at least most places. Natural log of x is not even defined at 0 or to the left of 0, but wherever it is defined, it's continuous. So say natural log of x is continuous on 0 to infinity. Basically, if you remember that library of curves that we studied during the pre-calculus phase of the course, you have a pretty good idea of where functions are continuous or not continuous. So we come to the very first of the 4 big theorems in Calculus 1. And it's called the intermediate value theorem. We often abbreviate this as IVT, intermediate value theorem. We've had some recent experience with another theorem, which is, I would say, in my opinion, not as important as the intermediate value theorem, but it gives us some idea of what the structure of the intermediate value theorem will be. Remember I said the theorem is sort of a true provable statement. Most of the theorems, all the theorems we'll study in this course have the form if, then some hypotheses, then conclusion. And the intermediate value theorem is no exception. So let's take a look at the intermediate value theorem. If, and then 2 things. 1, f is continuous on the closed interval AB. So if f is continuous on the closed interval AB, that's not a conclusion. I'm just saying if that's true, and my second hypothesis, k is a y value between of A and f of B. So if these things are true, I'm not saying that they are, but if these things are true, then here's the conclusion. There exists an x value C between A and B such that f of C equals K. I want this to be intuitively obvious by the time we're finished with it. Let's get ourselves a picture here. So we have these two x values, A and B. Just dot in vertical line A and a vertical line B. And at x equals A, let's say we're at this height. So there, that's f of A, whatever height I mark that at. And let's say at B we're over here. I'm not saying that f of B has to be bigger than f of A. I'm not saying that this y value has to be higher than this. It could be lower, it could be the same height. But I'm going to draw it on my picture as if it's higher. And K is any y value between f of A and f of B. So K is anywhere between here and here. Let me put it right here. I'll put it right up here. I'm not saying it's right in the middle. I'm just saying it's somewhere between f of A and f of B. So here's height K. Somewhere between f of A and f of B. So hypothesis 2 says K is y value somewhere between this height and this height. Hypothesis 1 says that I can draw the curve between this closed circle and this closed circle without picking up, in this case, my chalk from the blackboard. The conclusion says at some point between x equals A and x equals B, I have to cross this height. There has to be an x value in there where I cross that height. I think you can see that that's true. If this height is between the height I am at this end of the interval and the height I am at this end of the interval, and I cannot pick up my chalk from the blackboard, I have to cross this height. There's no way to avoid it. I can try to avoid it for a while, but sooner or later, I got to cross that height at least one place, maybe more, but there's got to be at least one place where I cross that height. It doesn't tell me where it is. Could be anywhere between here and here. Could happen more than once. I could go above this height and then below this height and then back above this height, and I could have my choice of C's. But there's at least one place where I cross this height. So let's say you're in an airplane and you're taking off from John F. Kennedy Airport in New York, which is almost at sea level. And let's say 15 minutes later, you're up at 30,000 feet. Then unless there's a button in the cockpit marked teleport, at some point you must have been at 10,000 feet. You had to have crossed the height 10,000 feet. There's no other way to get from 0 to 30,000 feet without crossing 10,000 feet or 18,000 feet or 24,000 feet. You crossed all the heights between 0 and 30,000 feet, unless the curve is discontinuous. So when you look at a theorem like this, you should automatically ask yourself, why are these hypotheses necessary? Why is it necessary to assume these to draw your conclusion? So in this case, it should be pretty obvious. Hypothesis 1 is certainly necessary. So if I start here at f of A, if I end up here at f of B, and K is somewhere in the middle, if the curve doesn't have to be continuous, there's no reason I have to cross this height. I could just go do, and then disappear here, reappear directly above it. Oops, they can't both be closed circles. And I never cross that height. So if the curve isn't continuous, there's no reason I have to cross height K. I could just jump over it using a jump discontinuity or a different kind of discontinuity. I could use an infinite discontinuity also. And likewise, if K isn't supposed to be between, if K doesn't have to be between f of A and f of B, there's no reason I have to cross this height at all. I can just start here and end up here. And if I'm taking off in that plane from JFK Airport, I go from 0 to 30,000 feet. There's no reason I have to cross the height 40,000 feet. Maybe we did. Maybe we had to get over a storm cloud. Maybe sometime between 0 and 15 minutes, we had to go up to 40,000 feet or higher than that. We crossed 40,000 feet because we had to avoid a storm cloud. But there's no reason, just by knowing you're at height 0, at time 0, at a height 30,000 feet 15 minutes later, there's no way from that information you can draw the conclusion that you were at 40,000 feet, and you may not have been. So does the main thrust of the intermediate value theorem make sense? Can you give me a thumbs up or thumbs down? Thumbs up, thumbs up. Awesome. So let's use the intermediate value theorem. I really wish I had more space. Prove that the equation x cubed plus x minus 1 equals 0 has a solution somewhere between x equals 0 and x equals 1. I'm not asking you to find it. I just want you to prove that it exists. And we're going to use the intermediate value theorem to do it. So the intermediate value theorem talks about functions. Let's come up with a function. So let's let f of x be x cubed plus x minus 1. I'm already given my two x values. Here's my, this is like a, and this is like b. So let's work out f of a. So f of a is equal to 1 cubed plus 1. Hang on for a second. Sorry. What am I thinking? F of 0 is equal to 0 cubed plus 0 minus 1, and that's equal to minus 1, of course. And f of 1 at the other end of the interval, that's 1 cubed plus 1 minus 1, and that's equal to 1. And this value, 0, that's my k. So 0 is definitely between f of 0, which turned out to be minus 1, and f of 1, which turned out to be 1. So when we're going to use a theorem, we have to check all the hypotheses. We have just checked hypothesis number 2, that this k value that we're interested in is somewhere between the value of the function at the left endpoint and the value of the function at the right endpoint. It's between minus 1 and 1. 0, I think we'd all agree, is definitely between minus 1 and 1. So we've checked hypothesis 2. So on this big vault door, we've just unlocked one of the two locks. Now we have to address lock number 1. Is f a continuous function? Well, f is a polynomial. We know polynomials are continuous everywhere. F is continuous everywhere. We don't care about everywhere. We only care about what happens between 0 and 1. So in particular, f is continuous between x equals 0 and x equals 1. We've just checked hypothesis 1. Both locks are unlocked. I'm going to jump over to here. Now we state the theorem. We don't state the theorem. We invoke the theorem by the intermediate value theorem. There exists an x value C between x equals 0 and x equals 1 such that f of x, and f of x was just x cubed plus x minus 1. Oh, sorry, such that, let me say f of c. We call this c because I call it c up here, equals 0. There's an x value c somewhere between x equals 0 and x equals 1, such when you plug it in, you get 0. In other words, you have a solution to this equation somewhere between x equals 0 and x equals 1. Let's say this question were to come up, hint, hint, on a midterm or a final exam, and you were sort of grading your own solution. Well, since we're using the intermediate value theorem to do this, you'd have to make sure that you checked both hypotheses. So you'd get a point for defining your function. Maybe you'd get a few more points for checking the values at the endpoints, the -1 and the 1, and saying that 0 is between them. So maybe a point for this, a point for this, and you said that 0 is between them. Now we've checked hypothesis number 1. Sorry, hypothesis number 2. You'd have to say something about continuity to get hypothesis number 1. You'd have to tell me that this function is a polynomial, and polynomials are continuous everywhere, and we don't care about everywhere, but we care about 0 and 1. You get a point for quoting the, not quoting, but invoking the intermediate value theorem, and you get a point for stating your conclusion, that there is a value somewhere between 0 and 1, such that when you plug it in to that, in for x, you get 0. So let's see. This question could be out of approximately 1, 2, 3, 4, 5, 6, 7, 8, somewhere at maybe around 8, maybe 9. And if all those parts are there, you get 8 out of 8. If you just said f of 0 is -1 and f of 1 is 1, so it's got to cross the x-axis somewhere between 0 and 1, that's worth maybe 2. So here's the picture. We just said we have this curve. When we plug in x equals 0, we're down here at height -1. And when you plug in x equals 1, you're up here at height 1. The basic idea is this is a continuous curve. We got to cross the x-axis somewhere between here and here, but we have to justify all this. So we did it. We used the intermediate value theorem. We were down here, we're up here. We had to cross the x-axis. We used the intermediate value theorem, and here's the complete solution. How's that so far? Is this good? Awesome. Thank you. I really do appreciate the feedback. It's very sad for me to have you so far away, so I really, really appreciate the feedback. Okay, let's move on to section 1.5. Hopefully you've got all this.
I have a question.
Grace over here first. I guess one of the few advantages for you this semester having remote classes is you can go and rewind me later and take a look again in case you missed something. So as usual, I'll have this posted either later today or tomorrow. So let's talk a little bit about infinite limits. So let's take a look at this function. One over x. As soon as I put that function down, you should have a picture in your head. 1 over x is a function that we've taken a look at. Hopefully you've committed to memory. We know what its graph looks like. It's a classic hyperbola. It has this branch over here. And it has another branch down here. It's in two pieces. And of course, it's not defined right at x equals 0. And let's consider the limit as x goes to 0 from, let's say, the right of 1 over x. We could build ourselves a chart the way we did all the way back at the beginning when we started talking about limits. So here's 0. We can plug in values. We can't plug in 0 to 1 over x, obviously, but we can plug in values close to 0, say from the right. 0.1, 0.01, 0.001. So these are our x values up here, and these are our y values, our f of x values. In other words, our y values. So if I plug 0.1 in, you plug that into your calculator, you take 1 over 0.1, you get 10. You plug 0.01, take 1 over that, you get 100. You plug 0.001 into your calculator, take 1 over that, you get 1,000. These numbers are getting big and positive. So we plug in a tens, we plug in a hundreds, we plug in a thousands. We can see that this curve is getting big and positive as we get closer and closer to x equals 0 from the right. And so up till now, we would have said the limit doesn't exist, but I think we would all feel comfortable saying that this limit, as x goes to 0 from the right, of f of x is plus infinity. Hopefully that feels like a fairly natural thing to say. And likewise, if we plugged in points from the left, numbers like negative 0.1, negative 0.01, negative 0.001, we get things like, we take 1 over negative 0.1, you get minus 10, minus 100, minus 1,000. And you can see that as you get closer and closer to x equals 0 from the left, the y values get closer, get bigger and bigger negative. And so hopefully it feels relatively natural to say that the limit as x goes to 0 from the left of 1 over x is minus infinity. And I further hope that if I ask you about the limit as x goes to 0, not specifying left or right, of 1 over x, knowing that you've already established that from the right it's plus infinity, and from the left it's minus infinity, and those two things are not the same, that you'd feel comfortable saying this limit doesn't exist, because these two one-sided limits are different. back up for a section to section 1.4, we're talking about continuity. So hopefully this seems okay. Let's take a look at the following functions. This is not about infinite limits, but let's say I have the function f of x equals absolute value of x divided by x. So another function that's not defined at x equals 0, because I have division by 0 if I try to plug in x equals 0. Now, I can plug in different x values and see what I get for f of x. Can't plug in x equals 0. But I could go ahead and plug in x equals, say, 1. Absolute value of 1 is 1 divided by 1. 1 divided by 1 is 1. I could plug in 0.5. Absolute value of 0.5 is 0.5. 0.5 divided by 0.5 is 1. If I plugged in 0.1, I get 0.1 over 0.1, that's 1. It doesn't matter what I plug in. I get 1 as long as what I'm plugging in is positive. But if I plug in a negative number, like minus 1, absolute value of minus 1 is plus 1. Plus 1 divided by minus 1 is minus 1. If I plug in negative 0.5, I end up with minus 1. If I plug in negative 0.1, I end up with minus 1. If you're wondering what this function looks like, it's 1 everywhere to the right and negative 1 everywhere to the left. This function looks a lot like this. It's not defined at x equals 0. It's 1 everywhere to the right, and negative 1 everywhere to the left, and it's not defined at 0 at all. But it's perfectly okay for me to say that the limit as x goes to 0 from the right of f of x, keep checking these y values, they're all 1, and the limit as x goes to 0 from the left of f of x, keep checking these y values, they're all minus 1. And if I asked you for the limit as x goes to 0 of f of x, these two aren't the same principle we employed over here. The limit from the left and the limit from the right are not the same. So this limit doesn't exist. Whenever the limit from the left and the limit from the right are different, the limit at the point definitely doesn't exist. Same principle. Over here we were talking about infinite limits. Over here we're not. I'm just talking about a plain old jump discontinuity. But there we go. Are there any questions? Well, thank you for your patience. I know I've gone a minute over. I will see you all on Monday. Have a great weekend.